the focus of today's talk is one near and dear to my heart, which is broadly, I guess, could broadly considered nucleophilic additions to metal alkene or metal unsaturated pi systems, and with a specific focus on Vocker type nucleometallation. Some of the Heck type chemistry, which we will cover at the end of class, we touched on already, as if you think back when we covered 1,2 migratory insertion. So that will be a little bit less of a focus today. Most of what we'll focus on is the so-called Wacker type nucleometallation and the mechanistic underpinnings therein. But I'll start out by introducing this theme in fairly broad strokes, and that is by familiarizing you all with a set of rules that are known as the Green, Davies, Mingos rules. Malcolm Green, a familiar name, Steve Davies, and Michael Mingos, 3 Oxford chemists. And these rules summarize empirical trends in terms of reactivity patterns for 18 electron metal complexes that contain multiple CC pi containing systems. And this is a framework to allow you to predict which sites are going to be most reactive. Now, I'm going to introduce these rules, and then what you'll see later in today's class are things that deviate from these, because, you know, with palladium 2 D8 square planar, it's a 16 electron, and thus doesn't necessarily strictly follow these rules, but these rules are good to know, and as a guiding principle for thinking about this reactivity mode broadly, and then we'll come back to this in the next lecture this week, which is on allylic substitution. So I'll just essentially read these out loud, but I think that's not necessarily that meaningful. But then we'll work through in problem of the day number 1. We'll work through a couple examples so you get a sense for this. Okay, so rule number 1 is that nucleophilic attack is preferred on even numbered polyenes. So 2, 4, 6 atom containing polyenes. And polyene here is used in a very general way to also encompass aromatic systems. Nucleophiles prefer to add to acyclic polyenes as opposed to cyclic polyenes. I think this is somewhat intuitive if you had to consider a case study like shown below, where you have benzene versus hexatriene, then intuitively you would think hexatriene is more reactive, and indeed that's the case. And then the third rule is that nucleophiles preferentially add to even hapticity acyclic polyene ligands at a terminal position and add hapticity acyclic polyene ligands. I think I'm missing some text here from my notes. Let me double check this. Acyclic polyene ligands at a terminus also is what I meant to say here. So here, think things like metal allyl species. If the metal is highly electrophilic, otherwise it adds to a internal site. So when you have ligands, for example, that are sigma donating and pumping electron density into the metal, it can actually bias nucleophilic attack to happen in an internal position of a metal alloy. That's not the most common thing, but it does happen. It's important to be aware of. And here's just a starred here is a way to visually sort of see these rules in summary form. So I'll leave this like this, so you can, if you want to jot this down, and then we'll cut to problem of the day number 1, which I've redrawn the complexes of interest here, but this is going to be done in poll format. So we'll poll and then just have very brief discussion. And this just asks you to consider for a generic nucleophile that is not specified, but we'd expect multiple different nucleophiles to exhibit the same reactivity patterns in this process. Which of these sites is preferred applying this Green, Davies, Mingos framework? So take a second to work through these. I think you'll find that actually these rules reflect hopefully what you've been developing in terms of your intuition for reactivity anyway, and just is sketched out in a more formal way. So I'll give you a minute or two to register your answers. Okay, we've got about 80% of people having voted, so take another 30 seconds, and if you don't know, then it's okay to guess as well.
Sure, I think it may be helpful to give at least one example of what metals you would consider highly electrophilic, as you have it written here, just so people can sort of get their bearings on what they would expect.
A metal that would be highly electrophilic. So I like palladium 2, for example, is most in terms of the like allylic additions, Tanner.
Yeah. I think I know a lot of people had questions about this before the midterm.
Okay.
So just to they can grasp their bearings on where to start looking for on the periodic table.
Okay. Okay, it looks like we have pretty good agreement with some dissent in some cases. So let's quickly go through. I'll call on volunteers, and you can maybe just unpack what you answered and why. And I'll just do this using my sorry, I got logged out. The panorama view of those in attendance. So Chunyu, what about A here? Are you there, Chunyu? Okay, I'm not hearing him, so let's move on. Nathan, what do you think?
So for this question, I picked 1, just because based on the trend that you wrote up there, it looks like a diene at the terminus.
Oh, sorry.
Sorry, Chunyu. Yeah, maybe you didn't unmute yourself. Why don't you do the next one then? Nathan, can you finish?
Yeah, so just based on the trend that you wrote out there, I would go for the diene at the terminus position.
Okay.
In this case.
Okay. Yeah. Sure. Good. Okay. Chunyu, what about? And most of the class agreed with you, Nathan. Chunyu, this one there was a little bit more disagreement. Maybe you can unpack this for us. Could you unmute yourself, Chunyu?
Could you hear me?
Now we can hear you. Yep.
Positives.
We're able to hear you. What was your answer for this one?
You're muted again, Junior.
Okay, Chinyu, it looks like you're unmuted. Do you want to give this one a try? Okay, looks like having some connectivity issues. Maybe we can circle back later. Junchen, how about you? What did you get for this one and why?
Yeah, I get 2 because first check the hapticity, and I found it's eta 3, eta 5, and eta 2. So I pick eta 2, which is 2.
Okay, and a fair number of people were thinking about 1, which would be like an allylic pathway. Why would you rule that out, or?
I think it's the same reason to the first one, because the only difference is olefin and allo group is on the same ring, but
okay,
it's different. Yeah.
And then the last one here, Huiqi, how about you?
For the last one, the 3 is the most easier to do the nucleophilic attack because it has the most reactive acetylene.
Okay. Very good. Yeah, and I think, you know, like, so some of the representative nucleophiles that you might see used here would be things like hydride, cyanide as a nucleophile. I think one of the key points is that by virtue of these complexes being 18 electron, it keeps the nucleophilic attack as being outer sphere in character, as opposed to having some pre-association, which we'll see muddies the water in terms of mechanism, like in the Vocker literature. Okay, any questions on this? I think the one thing that might be a little counterintuitive if you haven't seen it before is for complexes that contain like ethylene and a pi-allyl, which is the fastest reacting, you know, because those aren't the type of complexes that are super commonly encountered in synthesis. So just get familiar with those rules, and I think as we work through more examples, it'll become more and more second nature. Okay, so most of what we're going to. Yeah, was there a question, Carter?
Well, you might cover it. Sorry.
Okay, let's, yeah, if we don't get to it, Carter, then stop me later on. So most of what we'll focus on are metal-mediated alkene additions, and there are two general flavors here. So-called outer sphere processes and so-called inner sphere processes. The outer sphere processes are more akin to what we just saw, where the nucleophile is engaging, as it sounds, outer sphere from outside of the coordination environment of the metal. And then the inner sphere process, the nucleophile will first coordinate as a ligand on the metal and then be transferred via 1,2 migratory insertion. In either case, the intermediate that's formed is the same, depending on, well, let me unpack that. The stereochemical outcome of anti versus syn is different. Depending on the substituents on the alkene, stereochemistry that results could potentially be ablated. And we'll see how that manifests itself in several examples today, but as drawn here with simple ethylene, the intermediate that would be formed in either case is the same. In the case of inner sphere process, there's this requirement for an open coordination site, or rather that the ligand actually get onto the metal in the first place. And that's not possible in with some ligand frameworks like pincer ligands, for example. And then in terms of nomenclature, I will say that in the literature, if you're reading through papers, sometimes the waters here are a little bit muddy and people aren't always super clear in their terminology. But typically when you hear a term like nucleometallation, that's referring to being in this outer sphere mode, versus migratory insertion would signify being in this inner sphere mode. And those are occasionally in the literature also referred to as Vocker type and Heck type, respectively. That itself creates some confusion because Vocker type, as we'll see, can actually have multiple stereochemical outcomes associated with that reactivity paradigm, but people do use it that way. So I'm just telling you what people use. And then as a reminder, when we're talking about a metal olefin complex, there's a spectrum of reactivity here that depends on a number of factors, namely the oxidation state of the metal, the coordination environment of the metal. And so in one extreme are those that are mostly what we're going to cover today, where the metal is cationic, it's electrophilic. It's either in high oxidation state, so palladium +2, palladium +4, for example, or it's in neutral oxidation state, but still has electron poor, electron withdrawing ligands on it. And then the other end of the spectrum are metal olefin complexes that really behave more like 1,2 bis Grignard reagents. And I think this in organic chemistry, this might be familiar in the context of the Kalinkovich reaction, where you have like a ethylene equivalent complex with low valent titanium. The low valent titanium donates so much electron density to the organic fragment that it becomes 1,2 bis Grignard like and can engage carbonyls in that way. And so when you have metals that are anionic, electron rich, neutral, low valent, typically also there's a dichotomy here versus late metals being more electrophilic metal olefin complexes versus early metals being a little bit more nucleophilic at carbon. So again, echoing themes that we've seen before, like in Schrock carbines and so forth, Schrock versus Fischer carbines. And so this is the spectrum, this is the continuum, if you will. I'll even just draw this as such to emphasize that it's a continuum of reactivity, and these are the two extremes, and mostly what we'll focus on is this part of the continuum today. So in terms of historical organometallic chemistry, this is really one of my favorite stories, the development of the Vocker process and Wacker nucleopalladation reactivity as a driving paradigm in organometallics and in organic synthesis. And so this has humble historic origins, as many important discoveries and developments in science do. In the late 1900s, it was known from the work of Phillips that if you treated, let's say, let me redraw this. If you treated a mystery organic compound, remember that characterization techniques back then were not nearly what they are now. So very often you'd have some compound either in pure form or more commonly as a mixture, and you'd have no idea what the chemical composition was other than by things like taste or flame tests or these sorts of things to figure out actually what functional groups are. So one convenient test was to add palladium dichloride in water. And if there was an olefin present in your mystery molecule, you would know so, because you would form the corresponding aldehyde, and the indicator for them was that you'd get palladium black precipitating out. So mystery compound, add palladium chloride, see palladium black, that's an indicator that that mystery compound had an olefin in it. And that early observation then was revisited in a powerful way in post World War II Germany, and so now we can fill in the gap. And as you can see, that this transformation depicted here, this Phillips alkene test, this is not catalytic, and there's no obvious way for it to be turned over. The key challenge is that you'd need to reoxidize palladium 0, and that's exactly what they were able to do. So I'll draw out the final commercially developed Vocker process, and the Vocker process refers specifically to the catalytic oxidation of ethylene to acetaldehyde. And then Vocker type reactivity, or you'll hear Suji-Vocker, will cover all of this. That refers to this general reactivity principle where alkenes can be transformed into carbonyl-containing compounds or derivatives thereof. So the difference here, now it's the same elementary step, but the difference is in this cycle where you have copper 2, which is able to oxidize palladium 0 back to palladium 2. In doing so, copper gets reduced to copper 1, but copper 1 can then be reoxidized by molecular oxygen, even molecular oxygen found in air. So this is a truly, one of these magical catalytic reactions is turning dirt into gold. Well, if you think acetaldehyde is gold, basically some of the cheapest feedstocks available, air, and ethylene gas, and making a product of central importance to modern society, particularly at that time. And so just very briefly, some of the key features, or to contextualize the historical importance of this a little bit more clearly. So this work was it's interesting because it's a name reaction, Vocker oxidation, but the name is not the name of an individual. The name is the name of the company, Wacker Chemie. And the individual, the leader of the project team was a man by the name of Walter Hafner. This work was done in the 1950s in post-World War II Germany. The Vocker process is important because it's one of the very early examples of, if not the first, of homogeneous catalysis performed on industrial scale. And we've covered other industrially important early reactions like hydrogenation, hydroformylation, and reactions like Monsanto acetic acid process. This is right up there and arguably earlier than those developments. Certainly hydroformylation, hydrogenation, and Vocker process were all developed industrially within about 15 years of one another. And so again, to contextualize the importance, the reason this was a big development is that at that time, many industrially important compounds, for example, vinyl acetate, vinyl chloride, et cetera, were ultimately derived from calcium carbide, or ultimately derived from acetylene, which in turn was derived from calcium carbide. But that reaction to convert calcium carbide to acetylene is energy intensive and expensive. And so the motivation was, can we make these same sorts of products from ethylene? And this became especially important because a new refinery opened in Cologne in Germany, in this coal refining region of Germany called the Ruhrgebiet. A new refinery called the Esso refinery opened and granted access to huge amounts of acetylene, though there wasn't much exciting chemistry to do with it. And so the proposed transformation, which is kind of wacky. I mean, I'd leave you to think about mechanistically how you would think this reaction might take place. But the reaction they tried to do was using palladium on carbon, react this acetylene or this ethylene that they had large amounts of and O2 with the hope of making ethylene oxide. And as the story goes, when they ran this reaction and opened the reactor, they immediately knew that they had not made made ethylene oxide, and instead made acetaldehyde, because acetaldehyde has a very distinctive smell. So you open the reactor and you're like, wow, we didn't make what we thought we made, but we made something interesting. I think Barry Sharpless would like this story. And so then from that initial observation, there are huge engineering advances that also went into making this a commercial process. And I won't cover those in the interest of time, but at that time, the actual chemical reactors that were used caused various problems with this Wacker process. And so there need to be innovation in terms of using titanium reactor vats, and et cetera. That's a little bit outside of the scope of class, but just to contextualize the historical importance and the developments that went in both engineering and fundamental reactivity. I think particularly when you work more in feedstock interconversion or feedstock upgrading, the engineering advances sometimes are just as important as the fundamental chemistry. So let's take a look now at kinetics and mechanism. And I'll say now as a disclaimer that the mechanistic picture here is complex and frankly still the subject of debate to this day. So I'll try to paint the picture of sort of like the textbook representation of where the field stands, and maybe I'll have to update my notes in the years to come. And so in terms of the kinetics, there are two central regimes where you have different mechanisms at play depending on the chloride anion concentration in solution. So the industrially relevant conditions are these low chloride concentration conditions, and the rate here, or the rate law here, is shown. It has first order dependence on palladium pre-catalyst concentration or total palladium concentration, ethylene, and then negative second order dependence on proton negative second order concentration dependence on chloride, and negative first order on proton concentration. So what this tells you is that in the key rate controlling, yes.
Sorry, I don't know if this is happening for other people, but the screen shares weird.
Okay, one sec. Okay, yeah. Should be back online. I think the cable just got jostled. Thanks, Van. So this is the rate law, and then I'll talk about the what this sort of translates to. So this means that in the rate controlling transition state, we've we've got our catalyst. We've got a molecule of ethylene. We've lost a proton, presumably from coordinating water and losing proton. And we've lost 2 equivalents of chloride from the palladium to tetrachloropalladate species. And so we can draw that like sorry, let me. I think this is right. Let me put this up, and then I'll double check this. And then in the other conditions, which are high chloride concentration, we have a different rate law, and that rate law is a little bit simpler: positive order in palladium, positive order in ethylene, and then negative order in negative first order in chloride. And so the key dichotomy here obviously is what I alluded to before: inner sphere versus outer sphere, and how that actually manifests itself in terms of difference in the rate law. And what this means in terms of stereochemical outcome, which becomes more important when we talk about substitute alkenes, is that these high chloride, high concentration chloride conditions lead to this anti-pathway, and low chloride concentration conditions lead to syn pathway. And this is actually controllable by the reaction conditions. And so it's not always clear a priori which is going to be operable. And we'll see examples in the problems of the day where you actually have to make mechanistic determination of which is operable, because based on first principles, it's not necessarily clear. So then just walking through, after forming the key carbon-oxygen bond here, then again, either of these pathways, in the case of ethylene, leads to the same intermediate. And then in the classical Vocker process, you have a beta hydride elimination, which gives you a palladium hydride, which you can kind of think of as functionally equivalent to reduced palladium, but in practice, it needs to find a molecule of base to neutralize the palladium hydride to actually make palladium 0 to be reoxidized. But palladium hydrides themselves can react with O2, so it creates some mechanistic ambiguity there, and acetaldehyde. And one of the observations, we'll come back to this, is that a byproduct of the classical Wacker process, particularly when you have high chloride concentration, which normally you're introducing chloride through copper chloride. So when you have high chloride and high copper concentration, a common byproduct is a chlorohydrin that's formed from chloride acting as essentially in an electrophilic mode and reacting with the nucleophilic alkyl palladium. So given the industrial importance and also conceptual importance of this, as you can imagine, there've been a huge number of mechanistic studies that I'm not going to have time to chronicle all of them. But we'll just look at two important seminal pieces of work from the labs of Jan Beckvall and John Stille, both big figures in the area of organopalladium chemistry. And so let's first take a look at this experiment that Beckvall did, and I'll ask for some volunteers to help, where you take this doubly deuterium labeled ethylene. Let me zoom in here. Doubly deuterated ethylene, and then the reaction initiates in the same way as the classical Vocker process. And now this reaction, Beckvall's reaction, is performed in the presence of CO. So he took the Vocker out of its native habitat, kind of like taking an animal to the zoo to study it. He took it into the CO environment to try to learn something about mechanism. So what might happen here, Carter? What would you expect this reaction run in the presence of CO?
Could you have the CO coordinate to the palladium and then do a migratory insertion?
Love it. Okay. First step, I'll draw this and then delete it, as Carter said. Coordination of CO, and then what's going to be migratory insertion of the alkyl into the CO. Okay, anything that you suspect might happen from here, Carter?
Could you, I guess you could either do beta hydride elimination or some sort of lactone formation?
I like it. Okay, so you've got this nucleophile that's tethered intramolecularly. And this step is going to look a little goofy, and we can debate how to draw this. But maybe in terms of the organometallic chemistry involved, maybe the easiest way to think about this is coordination of the alkoxy, and then CO reductive elimination. But the way I'm going to draw this is just in shorthand as a coordination reductive elimination that effectively does this. So you're going to lose palladium 0 out, and the product sorry, I said this example was from Beckvall, but I think this is the Stille example. The TAs can correct me if I've got this wrong. I had it written in an ambiguous way in my notes. So now the key point is that you make a cyclic structure, and that allows you to then use NMR to determine the relative stereochemical configuration of where the deuteriums went. And in this case, that backtracking then is consistent with an anti-nucleopalladation mechanism. Okay, now thanks Carter, super. Let's take a look at this other set of experiments, where now the idea is from Beckvall is let's lean into this chlorohydrin pathway. So let's ramp up the amount of copper chloride, lithium chloride, and see if we could use that to our advantage. It's known that replacement of a carbon palladium bond with, or I think widely accepted that replacement of a carbon palladium bond with a carbon chloride bond takes place with inversion. And so you can do this experiment. And then backtrack and ask what happened in the key oxypalladation step, and in this case, also anti. Now, there's this overarching question with these experiments, and always, I think, in mechanistic experiments, is that does this reflect the actual industrial conditions? Because in both cases, you had to perturb the system from industrially relevant conditions. In the case of the Stille system, add CO. In the case of the Beckball system, amp up the amount of copper chloride. This is kind of like Heisenberg's uncertainty principle. To observe the system and learn something about the mechanism, you have to perturb it in a way that makes it unclear whether you're observing the insights that you get are reflective of the native system. And that I think is the essence of the challenge of deconvoluting this complicated mechanistic picture. Okay, so these experiments allow us to comment on the mechanism of the oxypalladation step, but they don't inform about the downstream step that we had talked about, namely this beta hydride elimination. So problem of the day number 2 will allow us to do just that. So these are some additional mechanistic experiments, and this we'll do in breakout room format. So Van, can you let me very quickly load the problem of the day, just in case anyone doesn't have this handy. So problem of the day number 2 asks you to consider these 2 deuterium labeling experiments. The first uses D2 water and sees no deuterium, and you see no deuterium in the product. The second uses tetradeuteroethylene, and you see this D4 containing acetaldehyde product. So think about that and think about what the implications are for the beta hydride elimination mechanism, and discuss that with your team for a couple minutes, and then we'll reconvene. Okay, Noor, I thought I saw you. When people are popping in, everyone's jumping all over. Noor, what did your team make from these experiments?
I guess what we've discussed was to essentially you would have beta hydride elimination as expected, but then reinsertion of hydride at the opposite site of elimination, followed by beta hydride elimination from the oxygen itself.
Okay.
Should grade.
And what specifically told you that? So let me draw what you just said as you're explaining. Noor?
Yeah. So you'd have beta hydride elimination, and then, yep, and then reinsertion of hydride in the opposite regiochem.
Okay, so now you're going to have hydride insert
at the terminal position.
At the terminal position, okay.
Mm-hmm. So at that point, you shouldn't have scrambling of deuterium and hydrogen, and then you beta hydride eliminate from the oxygen.
Okay. I'll just try to be crystal clear about where that hydride's coming from. Is that right, Noor?
Yep. That's what we discussed.
Okay. So yeah, one I think common mechanism that you might draw would be to draw beta hydride elimination to make this enol, which then could dissociate and get hydrolyzed under the reaction, or protonated under the reaction conditions, tautomerized. And if that happened, in the first experiment, you'd expect to see deincorporation at the alpha position, which you don't see. And you would expect, you wouldn't expect to see the D label migrate over as it does in the second experiment. So two pieces of mutually consistent data that indicate that this alkene, often this step isn't even really drawn on the catalytic cycle when people draw things out, but alkene dissociation from a palladium hydride it's not always a trivial process. And in fact, the palladium hydride kind of sticks around on the back of the alkene after beta hydride elimination and can reinsert and result in this alkyl metal chain walking, a theme that we've seen before in the class. So it's not always a given that the hydride is going to get off, particularly in the absence of base. Okay, any questions on that? Anybody get anything different that they wanted to put forward? Okay, now let's go through some things that might be of interest or relevant to synthetic, especially to synthetic chemists. So we mentioned the Vocker process, which specifically is the conversion of ethylene to acetaldehyde, but in the context of organic synthesis, that's not, I don't think anybody in either campuses is doing that reaction. And so there's a laboratory scale version that works with general terminal alkenes, and that's known as the Vocker process. The reaction conditions are shown here. The key change from what you saw before is the addition of DMF as a polar organic co-solvent. And so this reaction proceeds via a key, just an analogy to what we saw previously, a key oxypalladated intermediate that is formed with reliable Markovnikov selectivity that originates from the fact that in this palladium-2 alkene complex, you have delta plus charge accumulation at the secondary carbon atom because it can better accommodate delta plus. There's also a steric component for those who went to Cami Hall's talk, I think last week. You'll note that there's also a steric component to this, but in general, this is a useful mnemonic and to at least a first approximation is what's going on.
Can I ask a question about what we were just talking about in red?
Sure.
So you said it's no, like higher. Yeah. You said that it's hard to like dissociate the alkene from the palladium-2 hydride. So, but it's fine to dissociate when it's like a carbonyl palladium hydride. And is that, sorry.
Yeah. I mean, I think you hit the nail on the head, which is that an interaction between a carbonyl that is formed. I didn't draw this, but we can draw this. So you can either draw this as being coordinated through the pi system, or perhaps better representation is through the lone pair like this. This is going to be a weaker interaction, and so the off rate will be faster.
Okay, and then also like the hydride on the palladium is removed like through an interaction with copper, right? So is that also disfavored with the earlier complex?
Yeah, how does the palladium hydride get off? How does the hydride get off? So this could be, I think the way to think about this is reductive elimination of HCl, and then formation of palladium 0. That's what's getting reoxidized by copper. If that makes sense.
I see.
Yeah. Good. Yeah. Good questions, Camille. Any additional questions on that or the Vocker? So as I said, the Suji-Vocker is reliably Markovnikov selective. So much so that when you see these methyl ketones, you can immediately think of them as syntones. For alkenes or signaling elements to use of Suji-Vocker oxidation. But as you can imagine, there's been a lot of interest in overriding that inherent selectivity and getting aldehyde products. And there are a number of important reports, notably from Ben Feringa. I'll just highlight one from the Grubbs lab that came right before I joined as a postdoc, where there are a couple key changes from the classical Suji-Vocker conditions, notably the addition of T-butanol as a bulky alcohol solvent and nitrite. And so the mechanism here is murky, to be honest. But at least one thing that's proposed in the paper, and if you don't like this, take it up with Bob, I guess, is that this could be formed via. It's known, of course, that radicals will react at the terminal position of an alkene to give the more stable secondary radical. And so the thinking is that somehow nitrite is serving as an O atom radical and being delivered in this fashion that I've drawn in an intentionally ambiguous way. And so there are some O18 labeling experiments with nitrite that corroborate at least the fact that that's the O atom source in this reaction. But it is preparatively useful if you need to access aldehydes from alkenes, and has been used in total synthesis. As you'll see, most of the examples of Suji-Vocker oxidation are with terminal alkenes. Internal alkenes are more recalcitrant typically to participate in this reaction, and what you need to coax them to react is to tickle them with these biscationic palladium-2 species. And so the example I've shown here is also from the Grubbs lab based on a previous report from Canada. And the key here is to use HbF4 in the presence of a palladium-2 precatalyst, which can generate palladium, bis, acetonitrile, bis, trifluoroborate as a biscationic. And these biscationic palladiums are highly electrophilic, so they can coax even internal alkenes to react. Again, I think that it's just useful to know that if you need to use a Vocker oxidation in synthesis, that you know where to look. Maybe I'll just comment briefly that this aldehyde selectivity problem is still not totally solved. I think the best selectivities are still about 90%. So there is room for improvement there. Okay, to round out our oxygen nucleophile discussion, let's consider problem of the day number 3. And so I'll quickly exit my share and reshare so you can see the full reaction conditions. So in this case, we're reacting an internal alkenyl alcohol substrate with phenol now is our oxygen atom nucleophile, and under vaguely Wacker looking conditions in the presence of a chiral NN ligand. So a couple questions. One, what product would you expect based on the preceding discussion? And then 2, what is the mechanism by which it's formed? And then 3, to get back to this question about syn versus anti-nucleopalladation, how would you design an experiment to probe what's going on here. And you know, if you're going to say like deuterium labeling, then I'm going to follow up with the question of like, what position are you going to label, and how are you going to use that information to actually make a assignment? So consider those questions briefly, and I'll call on some volunteers here as I reshare. This just looks black to me. Let me try again. Okay, that looks good. Man's nodding. Okay, Jung, what do you think the product is going to be, and the mechanism?
Oh, well, I think the product would be a aldehyde, and you have the phenoxyl, the oxygen add to the alkene.
Which position?
Let's see. Well, I don't really know, honestly. I have to, I think possibly, I think maybe 2 if possible, but I would say at the one, I think it would be the one on the, oh, it's hard to say. Let me think a little bit.
Okay, so it's gonna, I think you're mostly there. So maybe you can just describe the mechanism. We might not need to draw it since it's similar to things we've seen, but
okay.
So how do you get the aldehyde from?
So the first step is the coordination of the palladium-2 complex to the alkene. Yeah, yeah. I'm not really sure whether the OH will also chelate or not, but probably not, because the OH is quite weak. So, and then the phenoxide will attack, and then you have two possible VGL isomer. So I would say the one.
Okay, maybe I'll draw the overall dipole of this molecule as a hint for which site would be preferred in the attack.
So I would say on the one on the left.
Okay.
And then you have the midtime eliminations.
Okay, and now it's the sequence we've seen before. Newer walked us through beta hydride elimination, reinsertion to get to the aldehyde. Okay, very good.
But I have a question.
Yes.
So do you think the OH will chelate to the palladium itself, and then it can reverse the GGL activity? So that
this is an example from Matt Sigmund's lab. Some people recognize the chemistry, and they've looked at mechanism fairly extensively, and they think the OH is not chelating. It's not directing through chelation, but it's through electronic induction. But if you know that they didn't know that until they dug into it. So you'd have no way of knowing just from the question itself.
Okay, thank you.
Okay, yeah, and maybe we'll ask for some thoughts on how to determine the syn versus anti-nucleopalladation. Any thoughts there, Tiffany?
I guess, would it be possible to deuterium label the alkene.
Yeah, which position?
I guess the 2 position.
The 2 position, okay. And then what do you expect to happen? Whoops, I drew the wrong position. This is what you're saying, Tiffany? C2?
Yeah.
And then we expect it to be here. Is that what you're thinking?
Yes.
And so in the intermediate, you're going to have deuterium here. And then you're saying that now you have 2 stereocenters. And the relative configuration should allow you to determine what's what. Now there's a caveat, which is that in the very next step, you're going to do beta hydride elimination and ablate this carbon palladium stereocenter. But as long as the palladium hydride that's made is bound to the same face with high fidelity, which they believe it is, then the stereochemical information could be maintained. Now there's another question I'll ask you, Tiffany, which is how would you determine using any analytical techniques what the relative stereochemical configuration is versus of OAR and CD here? You can't just take an NMR of an open chained alkyl and determine stereochem. So how would you get around this problem?
Is there a way to cyclize it?
Oh, brilliant. Wow. Perfect. Yeah. Exactly what the authors did. Cyclize, and you could imagine Friedel-Crafts chemistry, for example, cyclize the arene onto the aldehyde, make it a cyclic structure. And now once, as we saw above, in the work of Stille, once you have a cyclic product, then you can use NMR to make determination of relative stereochemistry. And this is very much similar to what the authors did. I think I think the starting material you proposed would potentially work, but it's just complicated by the fact you have to make that. And so I think they found that it's easier to make the one shown via reduction with deuteride. And then it's the same logic after beta hydride elimination. As long as the palladium deuteride stays on one face, then it's going to give you the same information. And then they cyclize it to read it out. Super. Thanks, Jung and Tiffany. Any questions on that? And that also brings us to the today's chemist of the day, who's the first author on this paper. I said the paper is from the Sigmund Lab. The first author of the paper is the chemist of the day, Nick Race, who is now an assistant professor at University of Minnesota. He did his PhD with John Bauer at Bristol before moving to Utah to work with Matt Sigmund, and has published his first, I think, corresponding author publication last year that you might have seen, some interesting arenium ion intermediate chemistry. Okay, very good. So let's go ahead now and move on to, I think, part of the power of palladium nucleometallation is that it's not just limited to oxygen. If it was, maybe you wouldn't hear so much about it. And so let's consider some cases where other types of nucleophiles can participate. And so actually one of the very, very first, possibly the first examples of CC bond formation with palladium is this example from Suji, where palladium cod dichloride is treated with a deprotonated malonate. I don't need the extra palladium here. And what would you expect would happen here, Carter, based on the discussion? This is a stoichiometric reaction, so don't worry about any subsequent steps that you might be imagining.
I would expect the anion to add into, I guess, however many equivalents of the, well, adding into the cyclooctadiene.
Okay. Very good.
Kiri?
Yes.
Do you mind if the question I was going to ask earlier, it's relatively related to this.
Sure.
For instances where you have some sort of diene rather than just an alkene, is there a way to predict whether you get some sort of 1,2 addition or 1,4 addition, or is it pretty dependent on nucleophile, metal, ligand, etc.?
It's a good question. I think the short answer is it depends. I think with palladium, you most commonly see 1,4. And ultimately what this, where that pre-geochemistry is determined is not in the initial nucleometallation step, but in the addition to the pi-al. And allylic substitution will be the topic of tomorrow's or Thursday's lecture. So we might come back to this, but with palladium 1,4 there are examples of 1,2. For example, if like the two components are tethered to one another and you can't reach around to react 1,4, it will react 1,2.
Okay, thank you.
Yeah. And so this example, as you can imagine, from especially the timing in the 1960s, really captured people's imagination. Coming fresh out of the development of the Vocker process, now you see the carbon CC bond formation can take place with a similar conceptual framework. But it took the better part of 40 years to develop this process into a catalytic version through heroic efforts by Ross Wiedenhofer, one of my heroes in organometallic chemistry. And that brings us to problem of the day number 4, which I've redrawn here. So this too gets at the same kind of theme as we've seen before. Maybe you're getting sick of it already. But we've drawn 2 products, so you can. I won't do the reshare here. I'll just draw out the products from this reaction. So this catalytic version was developed by Wiedenhofer. I'll draw the references shortly. And in a series of, in a follow-up study to look at the mechanism, they performed these deuterium labeling experiments. And so I'd like you to think about what the mechanism is, a plausible mechanism in light of these two data points. Both of them tell something slightly different. And so let's unpack this first one. Camille, what do you think here? I guess first, what kind of intermediate would be formed?
So first you coordinate the palladium to the alkene.
Yep.
And then with some sort of base, there'd be like, or I guess you could just have like tautomerization or some sort of base that deprotonates the.
Sure. Yep. Good.
And then you could do the nucleopalladation.
So you make the enol or enolate, depending on the other reaction conditions that I haven't specified. Let me redraw this. It's terrible. Okay, and then you have your palladium-bound alkene, which you said. It's going to activate it. Now you'll get attack, just like in the Suji example above. Stop me if I've got anything wrong here based on what you said, Camille. Okay, and now what? I'll add one more piece of information, which is that the authors find that this label is exchangeable under the reaction condition. So this can wash in and out because of the acidity. Okay. How do you end up getting deuterium on the opposite end?
I don't remember what the product was, but
let me have so deuterium in the end is observed at this position in the problem.
Okay.
So if you protonated directly at this stage, where would you expect deuterium to be?
Where the palladium is now.
Yeah, so you'd expect it to be here. That's not what's observed empirically. So how can palladium get from where it is to?
So you have to do like a series of beta hydrogen elimination or beta hydride eliminations and then reinsertions until the palladium is alpha to the ketone.
So chain walk, super Camille. Chain walk palladium to make a new palladium enolate. I'll draw it in C-bound form, but likely it's existing as equilibrium between C-bound and O-bound. And then now you deuterate off with the D plus that you formed in generating your enol. And the authors found that this position is not exchangeable. So the doubly activated alpha position is exchangeable, and this one isn't. Okay, and so this tells us basically in terms of mechanism that there's a chain walking process after nucleopalladation, chain walk to a position where it can be protonated most easily. And what about this second experiment? Eleanor.
Yeah, so I think it starts similarly to Camille's. Coordinate to the alkene, deprotonate the malonate, and then insert that into your alkene.
Okay. And what is the stereochemical outcome going to tell us about mechanism?
Whether it's syn or anti-nucleopalladation.
And which one is it in this case?
Syn, I'm not sure. I'm just gonna guess syn.
What do we think? Do people agree with this? And then let's see. Every year I say I'm not going to draw these ones that require me to think on my feet like this. Or to draw, maybe a better way to put it is to draw 3D on my feet like this. Is this right?
I think it should be anti-addition.
Carter's saying anti. So I think if you look at the stereochemical relationship between the nucleophile and the metal, they'll be anti.
Can you have a situation where the palladium is coordinated to both the enol alkene and the alkene of the olefin? For some, like when I'm trying to draw this, like the alkene, the palladium would be kind of stuck inside the ring. But is it possible to sort of have that concomitant?
Yeah, it's a good question. So basically, could you have the palladium form like like an ACAC, like a diketonate interaction as an activation mode? Definitely possible. So you could have, you could draw something reasonable where two palladiums are involved in the mechanism, or palladium 2 plus a different additive. And likely, palladium is binding to alkene, it's binding as ACAC. These are in equilibrium. Does that answer your question, Noor?
I actually meant that one palladium coordinating to both, and sort of. Okay.
Oh, I see. Yeah, I think it can bind in that pose, but I think it would be non-productive because it will situate the nucleophilic carbon. Like if you think about, here's the alkene and then palladium is my hand, then and it binds to ACAC over here. The nucleophilic carbon is going to be way where this curtain is, and there would be right. It would need to dissociate and then to engage. Sorry, I lost my, okay, there it is. Okay, so let's go through a few more examples with the remaining time we have left. So in addition to carbon-based nucleophiles, nitrogen-based nucleophiles can participate in this chemistry. And that was also known for a long time through pioneering studies by Ackermark. Ackermark is like the father of Swedish organopalladium chemistry, former supervisor of Jan Backfall, as well as Lou Hegedus. Hegedus was there for postdoc. So here's an early stoichiometric example where the authors are able to get aminopalladation across diverse alkenes and then carry forward these alkyl palladium species that are well-defined complexes, can be isolated, and do things like treat them with reductant to give the formal hydroamination product. And then Vocker type chemistry has also been rendered catalytic after these pioneering stoichiometric studies in the 70s. So an example here is from Shannon Stahl's group. You see the conditions are kind of similar to what we've done before. O2 as a terminal oxidant. For catalytic versions of Vocker, the types of nucleophiles that participate all lie in this sort of sweet spot pKa range of let's say between, gosh, I'm probably going to get this wrong, but 18 and 22 or something. So things like sulfonamides, phthalamides, anilines in some cases, amides, carbamates. Typically, that's the profile of nucleophiles that participate, because the problem is if you use truly basic amine coupling partners, the amine can coordinate to the palladium catalyst and attenuate its electrophilicity. That's why this reaction above couldn't be rendered catalytic because you're using these alkylamines that serve as catalyst poisons in a sense. So that's sort of the story in terms of other nucleophiles. And then we've already seen some examples of this in the Wiedenhofer work where we disengage, the catalyst disengages the organic fragment through a protonation rather than a beta hydride elimination. But there's actually a whole diverse array of transformations that can take place. So most of what we've seen today are these. So here I'm just considering, for the case of simplicity, these cyclizations where you have a nucleopalladation to form a cyclic structure and then react this further. When we react via beta hydride elimination, we get a structure that looks like this. We can also react with iodobenzene diacetate, which serves as a OAC plus source. And this can allow for a palladium 2,4 redox couple to make amino or amino oxygenated products or dioxygenated byproducts. So here I've simplified NUH as being an oxygen or nitrogen-based nucleophile. We saw an example of this type of reactivity already, where we can take advantage of the fact that CO can slip in quickly into these alkyl metal species, engage in migratory insertion and then reductive elimination. And then we also saw an example of this, where we protonate this off. And there's some interesting underlying redox here. If you think about it, this is a palladium 2,0 cycle. This is a palladium 2,4 cycle. This is a palladium 2,0 cycle. This is a palladium 2,2 or all palladium 2 cycle. And so the initial part is the same as what we have seen, this palladium 2 mediated nucleometallation, but then there's a diversity of things that can happen in different redox manifolds that can be accessed, and that's something that has continued to excite my lab. There's also an interesting twist on this, and this comes largely from the work of John Wolfe at University of Michigan, where you can generate a palladium 2 aryl species via oxidative addition. This is different than what we've seen before and actually connects more to Heck type reactivity. And this is actually sufficiently pi-Lewis acidic that it can coordinate to an alkene and mediate nucleometallation. And then now you have an aryl group nicely tethered intramolecularly for reductive elimination. And here the redox chemistry is a little bit different. It's a palladium 0,2 cycle. This part, if it's confusing, then don't worry, because it's thematically a little bit different than what we saw before. Okay, so let me just finish these last couple notes, and then this next part, beyond terminal alkynes, this will beyond terminal alkenes, this will tie in nicely to the allylic substitution chemistry anyway, for the reasons that Carter alluded to. So we'll pick it up there on Thursday. So I had shown this example where you can cyclize and protonate. Here's more specifically what this looks like. Here's an example from Forrest Michaels' group, where they take these alkenylamines, treat them with a palladium PNP pincer biscationic species, highly electrophilic. That triggers aminopalladation. And then now the carbon palladium bond is able to be protonated off triflic acid that's generated in situ from copper triflate. And then our group, I have to at least once in the class just put a plug in for our own group's chemistry. So please indulge me. So we've been able to render this sort of transformation fully intermolecular, and the trick that we play is by building the ligand into the substrate. And so in this case, we get now I give you full permission to judge me if I can't draw this correctly. So we get an intermediate like this. We've actually characterized these crystallographically. And now with nitrogen or carbon-based nucleophiles, they can attack here. Regioselectivity is controlled. Actually, that's an interesting story. Regioselectivity is believed to be controlled in the downstream steps, and this is supposed to be fast and reversible. At least that's our current best guess. And now in the presence of a proton, and in our case, we use something like acetic acid or benzoic acid as an additive. Now we can protonate off this carbon-palladium bond. And one of the key features that we found here is that the use of this bidentate auxiliary group actually suppresses beta hydride elimination because of how rigid these intermediates are by virtue of being bicyclic. Okay, I've already gone several minutes over, so thanks for bearing with me, and we'll see everybody on Thursday.